Tonight, we are going to talk about the smallest thing that can exist. Not the smallest thing we have found so far. Not the smallest thing our current instruments can detect. The absolute smallest thing that can, even in principle, exist anywhere in the universe. The floor of reality. The point at which space itself runs out of meaning. It is called the Planck length. And it is so incomprehensibly small that every comparison anyone has ever made to describe it immediately fails. But let us try anyway, because the attempt itself is part of the story. A human hair is roughly 1/10 of a millimeter wide. You can see it, you can hold it. It is the thinnest thing most people encounter in daily life without needing any instrument to confirm its existence. Now divide that hair into 1,000 equal pieces, and each piece is now 1 micrometer wide, the scale of a bacterium. You cannot see a bacterium with the naked eye, but you can see them clearly under a basic microscope. Divide one of those pieces into 1,000 again, and you are at the scale of a nanometer, roughly 10 times the diameter of a hydrogen atom. You need an electron microscope to see anything at this scale. Divide again by 1,000, and you are inside the atom, approaching the scale of the nucleus. Divide the nucleus by 1,000, and you are approaching the scale of a quark, the smallest particle we have ever detected. And then, you need to divide by another 100 million to reach the Planck length. Let that sit for a moment. We have divided a human hair by 10, then 1,000, then 1,000 again, then 1,000 again, then 1,000 again, and then by another 100 million, and we have finally arrived at the smallest meaningful length in the universe. The number is 1.616 times 10 to the minus 35 meters. Written out, it looks like an absurd number. A proton is 100 million trillion times larger than the Planck length. If you scaled a proton up to the size of the observable universe, the full 92 billion light-year sphere of everything we can see, the Planck length would still only be the size of a proton at normal scale. The ratio between a proton and the Planck length is roughly the same as the ratio between a proton and everything we can see when we look at the entire sky in every direction simultaneously. That is the scale we are talking about tonight. Not small in the way that atoms are small. Not small in the way that quarks are small. And small in a way that has no analogy that survives contact with the actual number. And at that scale, the universe breaks. Not metaphorically. Not in the poetic sense that things become counterintuitive or hard to visualize. The two most successful and most precisely tested theories in all of science, general relativity, which describes gravity and the large-scale structure of space-time, and quantum mechanics, which describes everything at the smallest scales. Both arrive at the Planck length and stop working. Not one of them, both of them, simultaneously, at the same place. The universe has a floor, and when you reach it, the rule book disintegrates. Let us start with how we found it, because the story of the Planck length begins not with a measurement, but with a thought experiment. In 1899, the German physicist Max Planck was working on a set of natural units. Not units defined by human convention, not the second defined by the rotation of the Earth or the meter defined by the circumference of the planet. Units defined by the fundamental constants of the universe itself, the speed of light, the gravitational constant, the quantum of action now called Planck's constant. Planck combined these three constants mathematically and found that they produced a specific length, not a length measured by observation. A length that falls out of the mathematics when you ask the question, what length does the universe itself consider fundamental? The answer was 1.616 times 10 to the minus 35 meters. A number so small it looks like a typographical error. Planck himself was not entirely sure what to make of it. He noted that these natural units would retain their meaning for all times and all cultures, even for non-human and non-terrestrial civilizations. He was pointing at something real. He just could not fully articulate what. It took most of the 20th century to work out why his number mattered. Here is what happens when you try to look at something smaller than the Planck length. In quantum mechanics, looking at something requires using light or some other form of radiation to probe it. The smaller the thing you are trying to see, the shorter the wavelength of radiation you need. Short wavelengths carry high energy. This is why X-rays can see through flesh. They carry enough energy to penetrate soft tissue. This is why particle accelerators need to be enormous. They are accelerating particles to extraordinary energies to probe smaller and smaller scales. To probe a length the size of the Planck length, you would need radiation with such a short wavelength that it would carry an almost inconceivable amount of energy. So much energy concentrated in such a tiny region of space that, according to general relativity, it would collapse into a black hole. Not a large black hole, a microscopic one, but a black hole nonetheless. And here is the consequence. The probe you sent to look at the Planck length would create a black hole in the act of looking. The black hole would swallow the information you were trying to obtain. You would learn nothing. The universe would actively prevent you from seeing below this scale by responding to your attempt to look with a gravitational collapse that destroys the very information you were seeking. This is not a limitation of our technology. It is not a limitation that better instruments will eventually overcome. It is a fundamental feature of the structure of reality. The universe is not hiding what happens below the Planck length. The universe is telling you, in the most direct physical language available, that the question of what happens below the Planck length may not be a meaningful question. Think about what that means. We are used to the idea that there are things we do not yet know, things that are currently beyond our instruments or our understanding, but which are in principle knowable. The history of science is a history of things that seemed unknowable turning out to be knowable with better tools or better frameworks. But the Planck length is different. It is not currently unknowable. It may be permanently, fundamentally, physically unknowable in a way that has nothing to do with the quality of our instruments. The floor is not just the floor of what we can measure. It may be the floor of what can be measured by anyone, ever, anywhere in the universe. Now here is where it gets genuinely strange. Because the Planck length is not just the limit of measurement, it is the point at which the two great theories of physics collide and destroy each other. General relativity is the theory of the very large. It describes how mass curves space-time, how gravity works across cosmic distances, how the universe expands, how black holes form and behave. It is one of the most precisely tested theories in scientific history. Every prediction it has ever made has been confirmed to extraordinary precision. The bending of light around massive objects, the slowing of time in gravitational fields, the existence of gravitational waves, all of it confirmed, all of it correct. Quantum mechanics is the theory of the very small. It describes how particles behave at subatomic scales, how atoms hold together, how light interacts with matter, how the fundamental forces work at their most basic level. It is the foundation of everything, from semiconductors to lasers to the chemistry of life itself. It is also one of the most precisely tested theories in scientific history. Its predictions have been confirmed to more decimal places than any other theory ever proposed. The problem is that they are incompatible. Not slightly incompatible, not incompatible in obscure edge cases. Fundamentally, structurally incompatible in their most basic assumptions about what reality is. General relativity describes a universe that is smooth and continuous. Space-time in general relativity is a fabric, infinitely divisible, with no smallest unit. You can always zoom in further. There is always more detail. The fabric is seamless down to any scale you care to investigate. Quantum mechanics describes a universe that is fundamentally discrete and probabilistic. Things do not have definite positions until they are measured. Energy comes in quantized packets. There is inherent uncertainty built into reality at every scale. The universe is granular and probabilistic all the way down. And these two pictures cannot both be completely true. At the scales of everyday life, and even at the scales of particle physics, the incompatibility does not matter much. We can use each theory in its appropriate domain without running into the contradiction. But at the Planck length, both theories must apply simultaneously. Gravity is so strong at this scale that general relativity is essential. Quantum effects are so dominant at this scale that quantum mechanics is essential, and they give contradictory answers about what reality looks like. Space-time itself at the Planck scale is expected to become quantum, not just described by quantum mechanics, actually quantum, fluctuating, probabilistic. The smooth fabric of space-time that general relativity describes should dissolve at this scale into something no current theory can properly describe. Physicists call it quantum foam. And it is worth spending a moment on what that phrase actually implies, because it is one of the strangest ideas in all of science. Imagine the surface of the ocean seen from an aeroplane at cruising altitude. From that height, it looks perfectly smooth and flat, a continuous, unbroken plane of blue. Now descend. At a few hundred meters, you begin to see waves. At sea level, you see the waves in detail, their crests and troughs, the spray at their edges. Now imagine diving beneath the surface and continuing to zoom in until you are at the scale of individual water molecules. The smooth ocean has resolved into discrete particles bouncing around at enormous speeds. The smoothness was always an illusion of scale. Quantum foam proposes that something similar is true of space-time itself. At the scales we experience, space-time appears perfectly smooth and continuous, the stage on which everything happens. But at the Planck scale, that smoothness is expected to break down. Space and time themselves would be subject to quantum uncertainty, fluctuating violently, boiling with virtual geometry, topology changing from moment to moment. Tiny black holes and wormholes might be constantly forming and evaporating at this scale, the fabric of reality churning with a violence that bears no resemblance to the calm space-time we inhabit. The stage itself, at this resolution, is not a stage at all. It is a storm. A seething, high probabilistic, constantly fluctuating foam of geometry that our language barely has the tools to describe. And here is the most important thing about quantum foam. We have never observed it. We cannot observe it. We know it must be there. The mathematics demands it. But every attempt to detect Planck scale structure in the fabric of space-time has found nothing. Not because it is not there, but because reaching that scale experimentally is so far beyond any technology we can imagine that the gap between where we are and where we need to be makes the gap between a stone axe and the James Webb Space Telescope look trivial. We know the storm is there. We cannot see into it. Now here is where the most interesting speculative physics lives, because the Planck length is not just the limit of current theories. It is the target of every serious attempt to build a better one. String theory, the most developed candidate for a theory of everything, proposes that at the Planck scale, the point-like particles of quantum mechanics are replaced by tiny vibrating strings of energy. The strings have a minimum size, roughly the Planck length, and different vibrational modes correspond to different particles. The Planck length is not a wall in string theory. It is the scale at which the fundamental structure of reality is revealed. The strings are the pixels. Below the Planck length, the question of what a string looks like simply does not apply any more than you can ask what a pixel looks like if you zoom in beyond its resolution. Loop quantum gravity, an alternative approach, proposes that space-time itself is quantized at the Planck scale. Space is not infinitely divisible. It is made of discrete units, each one roughly Planck length in size. The smooth fabric of space-time that we experience at everyday scales is an approximation, like the smooth surface of a screen that looks continuous from a distance but resolves into individual pixels when you get close enough. In this picture, the Planck length is not just a limit, it is a fundamental grain size, the resolution of reality itself. Neither of these theories has been experimentally confirmed. Neither may be correct, but both of them, from completely different starting points and using completely different mathematics, arrive at the same conclusion. The Planck length is not arbitrary. It is not a human convention. It is not a limitation of our instruments. It is the scale at which the universe is structured at its most fundamental level. Whatever the correct theory of quantum gravity turns out to be, it will have the Planck length built into it at the foundations. The most remarkable thing about the Planck length is not how small it is. It is where it comes from. It is not derived from any observation of a specific physical phenomenon. It is not the size of any particle that has been discovered. It is derived entirely from the fundamental constants of nature, the speed of light, the gravitational constant, and Planck's constant, combined in the only way that produces a unit of length. The universe's own rulebook, applied to itself, produces this number. It is as if you took the three most fundamental facts about the universe and asked them what the smallest meaningful length is, and they all agreed on the same answer. That agreement feels significant. It feels like the universe is pointing at something. It feels like the Planck length is not just a limit of our knowledge, but a feature of the universe's own architecture. A pixel size, a grain size, a resolution, the level at which reality is rendered. And here is the last thing I want to leave you with tonight. We are the first civilization in the history of this planet to have found this floor. Not by going there, not by measuring it directly, but by combining our deepest theories about gravity and quantum mechanics and arriving, through pure mathematics, at a precise number for where space itself stops being divisible. Max Planck calculated it in 1899 without fully knowing what it meant. A century of physics has slowly revealed what it means. It means the universe has a grain, a resolution, a level below which the question of what exists becomes not just unanswerable but possibly meaningless. We cannot go there, we cannot see it, we cannot build an instrument that reaches it. But we know it is there, and we know precisely where it is, and we know that when our best theories arrive at it, they stop working. The most precise map in the history of science points to a location that no physics can currently describe. That is not a failure. That is one of the most extraordinary things our species has ever discovered. We found the edge of the knowable, not the edge of what we currently know, the edge of what can in principle be known by anyone with any instrument at any point in the future of this universe. And what lies beyond that edge, whether space is quantized, whether the fabric of reality has a grain, whether the universe is a smooth continuum or a vast and ancient pixelated structure rendering itself one Planck length at a time, remains the deepest open question in all of physics. The smallest possible thing is right at the boundary of everything we understand. And what it is doing there, what it is made of, what rules it follows, nobody in the history of this planet has ever known. Good night.